We were dealing with springs in the previous class, people, and we saw how to find out the equivalent spring constant in parallel. So whenever the springs are in parallel, in order to find out K equivalent, you have to add up the individual Ks. So for a two spring case, it will be K equivalent is equal to K1 plus K2. And we saw two cases, one where the two springs were on the same side and they were in parallel, and the second in which the springs were in the opposite side and they were still in parallel. And we understood that this is also a parallel case because the spring forces will add up. As the block moves to the right, the orange spring as well as the blue spring both will exert forces on the block in the leftward direction. So the orange one will try to pull the block and the blue one will try to push the block, and the two forces add up, so the spring constants will also add up. A follow-up problem can be a very simple extension of this. What if you have got a system of 3 springs? So let's say you have got an arrangement like this, where you don't have the top surface, and you've got a block somewhere that can move around, and the block is placed somewhere here. It is a block, it can move around somewhere, and this block is attached to 3 springs. Maybe there is one orange spring on the left which has got a spring constant K1, then you've got a green spring on the left which has got a spring constant K2, and then you've got a blue spring on the right that has got a spring constant K3. And I ask you, what can be the equivalent spring constant of this system? What is the equivalent spring constant of this system? What will you say, people? So from the previous experience, you now know that K equivalent will be K1 plus K2 plus K3. That's all. So now, having done this, let's move on to springs in springs in series. So let's move on to springs in series. And series means that the springs will be attached one after the other. So you will have a system where, let's say, you have got a support on the left hand side somewhere. So you've got a support here, and you've got one pink spring attached to the support and it ends, and then there is another orange spring attached to that pink spring, and then to the orange spring's other end, the right end of the orange spring here, we have attached a block. So you've got a block kept here like this. It is attached to the orange spring, and what you do is you have the spring constant. So the orange one has got a spring constant K2 and the pink one has got a spring constant K1, and I'm interested in finding out the equivalent spring constant of the system, which means if I wanted to represent this entire system using one single spring, let's say I've got a blue support and I've got a single light blue spring, let us say, which has got K equivalent as its spring constant, and to this one I attach the block. Right. Then the thing that I'm interested in asking you is, what should be the value of K equivalent so that the behavior of this system, the one with the blue spring, is exactly similar to the behavior of this orange and pink spring system, the one on the top. And how will you figure out the value of K equivalent? The process is simple. We know that if we apply a force F on this block towards the right hand side, let's say we have a force on the brown block towards the right hand side, then this force will be able to displace the brown block towards the right hand side. This force F, it doesn't start at a value F, because if it starts from a value F, there will be oscillations. We don't want them. So this force maybe starts from a negligible value when the springs were unstretched, the springs were in their natural length, and this force gradually pulls this block to the right and keeps on increasing. And finally, when the block stops somewhere, the force has attained a value F. That is what we mean. So the block moves to the right somewhere here, and after being displaced from the equilibrium by an amount x, right, so this was the previous equilibrium. After being displaced from that point by an amount x, the block is at rest at this place, and a force F is acting at the right end of the block like this, and this force has to be applied in order to keep the block at this place, because the moment you remove this force, the block will go back, right? So we can say that a force F is required to maintain a displacement of the block equal to x from its mean position. In the second case also, if I displace the block by an amount x, and if I have to apply the same force F to maintain that displacement, then I will be able to say that the spring here is equivalent to the two springs in the first case. They behave in exactly similar fashions. So what I want to happen in the second case is, when the block has been displaced by an amount x again, the force that should be required to hold it in place should still be equal to F. And I want to figure out what value of K equivalent will satisfy this criteria. Now, one thing to note is that the springs won't have a displacement x. One of the springs will have an extension maybe of x1, the other will have an extension of maybe x2, such that if you add up the two extensions, you should get this x here, which is the total extension really. So let me say that the first spring, the pink one, has an extension of x1. The orange one has an extension of x2. Such that for the original system, one of the equations is, for the original system, x is equal to x1 plus x2. Let's write that as equation number 1. Let us also try to figure out what equation will be satisfied in the second case. In the second case, for the equivalent system, so I'm going to write that on the right hand side itself. For the equivalent system, F should be equal to K equivalent times X. Let's keep it in our hands. That's equation number 2. And let's have a look at the first system and try to draw FBDs. Let us try to draw the FBD of the block, of the orange spring, and of the pink spring. The block, let's start with the block on the extreme right. So let's say the block is on the extreme right somewhere here, and the block will have a force F acting on it towards the right, and the block will have a force acting on it at the point where the orange spring is connected to it, and because the force is exerted by the orange spring, it will be K2 into X2. And because the orange spring has extended, orange spring wants to go back to its natural length. So the orange spring is going to pull on both of its ends. A spring tries to pull both of its ends in, or it tries to push both of its ends out if it is trying to go back to its natural length. So since the orange spring had suffered an extension, therefore the right end of the spring as well as the left end of the spring will try to move in such a manner that the spring goes back, it becomes smaller. And the force on this block on the left hand side can be written as K2x2. Fine. Now let's have a look at the orange spring itself. Let us draw the FBD of the orange spring, and let us draw it here somewhere. So here is the orange spring, and the orange spring will be acted upon by a force on the right hand side because of the block, Newton's third law. So the spring was exerting K2x2 on the block will be exerting K2x2 on the spring. So there will be a K2x2 on the right hand side. This is by the block, And on the left hand side, the orange spring is attached to the pink spring, and so it will be pulled by the pink spring because the pink spring also wants to become smaller. It wants to go back to its natural length. So you will have K1x1 force acting on the orange spring. So this is K1x1. And let us try to draw one FBD of the pink spring. And the FBD for the pink spring will look something like this. On the right end, the pink spring is connected to the left end of the orange spring, and so they must exert equal and opposite forces on each other. The force that is exerted by the orange one on the pink one is actually K2x2. So you know that this guy will be K2x2. This is by the orange spring on the pink spring, and the pink's left end is attached to the support, and the support will be exerting a force on the pink spring in the backward direction. If that support is not present, then as you apply a force on the block and the two spring system will start accelerating towards the right. So there will be a force by the support in the leftward direction. Let me say that that is some F support. And all these springs are in equilibrium, right? So the pink spring as well as the orange spring and the brown block, everything is in equilibrium. So then I can say for equilibrium to be satisfied, F support must be equal to K2x2, at least for the pink spring. For the orange one, K1x1 should be equal to K2x2, and for the brown block, K2x2 must be equal to F. So therefore, you will get a series of equations that say F support is equal to K1x1 is equal to K2x2 is equal to F external. This is the final force that you had applied. So you get x1 is equal to F by K1 and x2 is equal to F by K2, which you can use in the first equation here. So inserting these two in the first equation, let me call this set of equations the third equation. Use 3 in 1 and you will get x is equal to F by K1 plus F by K2. And we know what x is from the equivalent system also. So for the equivalent system, we have got one equation, F is equal to K equivalent into x. So from there I can find out the value of x, that is F by K equivalent. So x is F by K equivalent. I can say that this entire system is equal to F by K equivalent, and then you will get 1 by K equivalent is equal to 1 by K1 plus 1 by K2, and plus the series will go on. So if you have got n number of springs in series, the summation will extend up to n terms. So 1 by K3 plus 1 by K4 and so on up to 1 by Kn. So please keep in mind that whenever you have springs in series, their equivalent spring constant is found by adding the reciprocals of individual spring constants and then equating it to the reciprocal of equivalent spring constant. And this is exactly opposite to whatever happened for resistors, and this is from your class 10th knowledge. So you can easily keep whatever is happening to springs in mind by keeping in mind that they are exactly opposite to resistors. And is there any physical reason behind it? Maybe it's because springs are energy storing devices while resistors are energy dissipating devices. That's not a very convincing answer, but yeah, physically we have seen that. And then in class 12 electrostatics, you will encounter another energy storage device called the capacitor. And the capacitor follows the same pattern as springs. So maybe energy storage works in a different way and energy dissipation works in a different way. You've got a spring and the spring has got a length L. So its natural length is L. And its spring constant is K. And this spring is broken into two parts. Let us say that we have broken it up here somewhere so that the ratio of lengths is given, right? So you know L1 is to L2 ratio, and they want you to find out what are the spring constants of those two parts. So the question is, the spring has been cut into two parts of lengths L1 and L2. Find out the spring constants of those two parts. Right, now how do we start attacking this kind of a question? We can probably feel, and it's an intuitive feeling, that for the smaller spring, the spring constant should be larger. Because if I give you two springs of the same size, that's of the same radius, so you've got two springs of the same radius, and one of them is longer and the other one is shorter, you know that it will be easier to pull the longer one and it will be more difficult to pull the shorter one. So that means probably the shorter one has got a greater value of K. K is the stiffness of a spring, right? It shows you what is the amount of force that you need to apply to give a unit displacement, and K has units of Newton per meter, right? So we know that we'll have to apply a greater force to extend the smaller one and a smaller force to extend the larger one. So maybe K's will be inversely proportional to the length somewhere. So we expect the smaller one to have a greater K, but then there is no way that we can really say that that's happening, and there is no way that we can say that it will be just length power 1, and it may be inversely proportional to length square or something. So we will have to go mathematical, and what we can do now is we can try to do a small experiment, right, with these two springs. Of course, before we cut, it was a part of the same spring. So we can do a very small experiment. We can apply a force on one end, we can keep the other end fixed, and we can try to see the behavior of the spring. So let us say you have got a support and you have fixed the spring to that support. This is the spring fixed to the support, and what you are going to do at the right end is apply a force F in the rightward direction, and because of this force, the spring will undergo some extension. The extension can be easily found out. Extension will be F by K, where K is the original spring constant, right? So let me call it delta L. This is the total extension, and I can maybe make a guess that if the spring is linear, this extension will be uniformly distributed throughout the length of the spring. What I mean is this: if you break up the spring into two equal parts, and then you look at by what amount has the left part extended and by what amount has the right part extended, maybe you will get the answer that the left and the right parts both have an extension of delta L by 2, so that the total extension is delta L, right? So we can go for that. We can also prove that result in a slightly different way. We can try to break a spring into exactly two parts, equal halves, and then we can say that because the first half will be exactly like the second half, they will be symmetric and the spring constants must be equal, K dash and K dash. And then we can say that if we are applying a force F on this system, which is then a system of two springs in series, then their extensions must be the same. So we can argue like that also. But a very intuitive way of saying that is, if I take the spring and break it into two parts, half, then the first half is going to have an extension of delta L by 2, the second half is going to have an extension of delta L by 2. If I break it up into some other ratio, if I probably break the spring, so I have got the spring here, and the one on the left I break into two equal parts, then I can say that the extensions will be delta L by 2 and delta L by 2, and the right one, if I break in maybe the ratio 1:3, so I break it up into two lengths. The first one is 1/4 of the length and the other one is 3/4 of the length, so 1:3, then I can say that probably the extensions will also follow the same ratio, and the extension here will be 3 delta L by 4, and the extension of the left part will be delta L by 4. If I add up the two extensions, I'm still going to get the total extension of the original spring. So that gives me a method to attack this entire problem. Suppose I have to break this entire spring up into two parts whose lengths are L1 and L2. Then I know the ratio of lengths. So I take this spring itself and I copy it and I paste it here, and I say that the ratio of first length to the second length is L1:L2. So the ratio of extensions will also be that. The extension will be delta L into L2 by L1 plus L2 for the longer part, and the extension will be delta L times L1 by L1 plus L2 for the shorter part. And if you add up the two extensions, you are still going to get the total extension delta L. The left end of this spring has been fixed to some support, and the right end was actually pulled by a force F. So there is a force F at the right end, and the support force will also be F in the opposite direction. And the force existing in these two portions will also be F individually. So anywhere along the length of the string, the force is going to be F. So then I can say that a force F causes an extension of this much, delta L into L2 by L1 plus L2 in an original length L2. Right, and the same force F causes an extension of delta L into L1 by L1 plus L2 in a length L1. So F causes an extension of delta L times L1 by L1 plus L2 in the first chunk or the first part of the spring. So therefore the spring constant of the first part will be F by the extension in the first part, and that's delta L times L1 by L1 plus L2, and you will be getting something like F times L1 plus L2 divided by delta L times L1. Not a big deal. And the same kind of equation for the second part. F causes an extension of delta L times L2 by L1 plus L2 in the second chunk. So therefore the spring constant of the second chunk, K2, will be F, the force, divided by the extension delta L times L2 by L1 plus L2, which will give you F times L1 plus L2 divided by delta L into L2. And from these two equations which I have here on the screen, I can try to figure out the ratio K1:K2. So now K1:K2 will be, and if I find the ratio of the left hand sides, I can find the ratio of the right hand sides. F and L1 plus L2 etc. will cancel out, delta L will cancel out, and L2 will flip up. So K1 by K2 will be L2 divided by L1, or you will get K1 L1 is equal to K2 L2. And I can associate this with the total spring also. For the total spring, I can say that F would have been equal to KL, right? It would have been equal to K delta L really, right? So when I insert all that, I will get K1 L1 is equal to K2 L2 is equal to KL. Or if you don't want to go to that route, you can say that I've got two springs, right? You can say that I've now got two springs. So this system, you are now saying, is equivalent to a system of two springs, with K1 being the spring constant of the first part K2 being the spring constant of the second part, and you know the relation between K1, K2 and the total spring constant. The total spring constant of this system should be equal to K, but then these two springs are as if they are attached in series with each other. So therefore 1 by K equivalent, which is 1 by K of original spring, is equal to 1 by K1 plus 1 by K2. So you now know the ratio of K1, K2, or you know this one equation. You know the second equation between K1, K2. You have two equations, two variables. You can determine the values of K1, K2, and you will get the answers. So either you can use that scheme, or you can straight away use the fact that K1 L1 will be equal to K2 L2. It will be equal to KL. Right, we can say that. So therefore, the two schemes are either use K1 L1 is equal to K2 L2 with 1 by K is equal to 1 by K1 plus 1 by K2, or use K1 L1 is equal to K2 L2 is equal to KL. Right. So you can either use this or that, and you can figure out what are the spring constants of those two parts.